right, so for the back of the worksheet, we start talking about these related rate problems. We're going to set up a relationship using the variables in the situation. Drawing a picture is going to be a huge help for you in imagining what is happening change-wise. You're always going to differentiate with respect to time, and then you're going to use implicit differentiation to be able to find these rates. So if we look at example 3, I'm using a ladder to paint my house. The ladder is leaning against the house when I decide to pull the base of the ladder away from the house. So this distance here is going to be getting bigger. So as my ladder moves away from the house, notice what is changing and what is not changing. The length of the ladder is always going to be constant, but how far it is up and down the house and how far it is away from the house is going to be changing. So this A and this B height. So when I go ahead and I find my derivative, 2 times A, and then the derivative of A is dA dt. So this squared, using our same power rule, 2A dA dt plus 2B dB dt. And it's going to be equal to 0 because the derivative of this C value is constant. So that's why it's going to be 0. So here's what's going to happen in our next lessons. We're going to be substituting in either the rates of change, and we're going to be looking at these values, and then we're going to be able to solve for what it is we're missing. Right now, we're just practicing the implicit differentiation to be able to do that. All right. Looking at example 4, the length and width of a rectangle are increasing. Relate these rates of change with the rate of change of the area of the rectangle. So when I look here, I can see that my width is going to be getting bigger and my length is going to be getting bigger. So as I look at my rectangle changing, this length area is going to be expanding and this width area is going to be expanding. So if I want to know the result of the change in the area with respect to time, I'm going to need to take the derivative, and this is a product. So I'm going to have my first term times the derivative of my second plus my second term times the derivative of the first. And that's all I need to do right now, because once I get this data, then I can answer whatever question they tell me. If I figure out the rates, how quickly they were changing, the original values, and then I can look at how that area is changing as a result. All right, let's talk about blowing up a balloon. A spherical balloon is expanding. Relate the rate of change of the surface area of the balloon with the rate of change of the radius. So I know that the surface area of the balloon is going to be equal to 4 pi r squared. And as this balloon blows up, this radius value is going to be getting bigger along with it, assuming that it's spherical. So area is equal to 4 times pi times r squared. Now 4 pi is a coefficient. Remember, pi is a constant. So we can just, when we take the derivative, the change in the area with respect to time is going to be equal to 2 times 4 pi is 8 pi, r to the 1 less power, and then the rate of change of the radius. So I can look at the rate of change of the radius as a result of the rate of change of the area. So in future lessons, we're going to have some values to plug in and go ahead and solve and answer. For now, we're just practicing the implicit differentiation. And that's it for this